darnos una plática sobre investigación que está realizando con nuestra colega. Y como verán, está ahí el título de la plática, y podría decirlo todo excepto por la parte en latín, entonces no voy a hacer el ridículo que nada más puede decir.
Thank you. Thank you very much. Good evening or good morning, I don't know. I'm sorry that I do not, I'm sorry that I will not be able to speak in Spanish. My Spanish is very, very poor, and I would like to thank the invitation from Roberto and from Lourdes, and it's really very, it's a pleasure to stay here in UNAM. In fact, I will try to present these results, and the main point of my approach is to link mathematical modeling and data. Due to that, be here. No? It's not going down. It's stuck. Eu não testei.
Yeah.
Here.
Okay. Yeah.
It's here. Okay.
Right, yeah.
So, due to that, our team is an interdisciplinary team. There are people from hard science, also Gustavo and Lourdes and Cláudia Ferreira, and people from life science. And the bold one are the students involved. Here we have two of them, Daniel and Flavia, that are visiting UNAM with us to work together. And in fact, we are very motivated by the heterogeneous patterns in data that we observed. And I will try to present two problems that in some sense are related to each other. One problem is the co-circulation of virus transmitted by Aedes, mainly Zika and dengue. And we will use a deterministic model that was proposed by Esteva some years ago, and the stochastic version. And the main point is that we would like to analyze the herd immunity effect between dengue and Zika. This is an important question nowadays for people, because people from public health, because they would like to know how one infection affects the other from the individual point of view and also from the populational point of view. And the other problem is another work related to the vaccination strategy against dengue. We use a partial differential equation, also based in a work of Gustavo and Lourdes, and we analyze a lot of data, and we would like to estimate the optimal age of vaccination. There is a difference between the work of them, that since we analyze a lot of cities in Brazil, we are applying the method from numerical point of view. So it's easier to fit some data and to estimate the optimal age. But why are they so related? Because in fact, it's not clear for people, and it's another important question, is that how the dengue vaccine, an effective dengue vaccine, may have some kind of effect on Zika outbreaks. Why do we analyze dengue and Zika? Because they belong to the same flavirus, and there is a kind of cross effect. And the point is that, if, for example, it's possible that there will be a very strong Zika outbreak due to a very efficient application of dengue vaccine. We do not analyze this problem, but this problem is the motivated of these both problems that we are analyzing. Then what's the state of art? As most of you know, we have a lot of diseases that are transmitted by Aedes aegypti, dengue, yellow fever, Zika, and chikungunya. And now, besides the vector control, there is a vaccine, a good vaccine against yellow fever, but not yet a vaccine that, a very good vaccine against the 4 serotypes of dengue. Okay, for example, there is a vaccine that is approved in Brazil, but it's not recommended to individuals without previous dengue infection. There is some kind of reaction, and the public health system in Brazil, they stopped to apply the vaccination to these people. There were some problems. And this vaccine was approved at the beginning of 2015, and at the same time there was suspected cases of Zika in the northeast of Brazil. I remember that I was here in Mexico, and at the end of my last talk in 2015, I talked about it, that there were some suspect Zika cases, and people are very confused in Brazil, a kind of very huge epidemics. And at the end of that year, there was an epidemic of microcephaly cases. It was a very, very dangerous situation. A lot of children, and with all other kind of anomaly, and it was proved in the literature, it was proved that there is a relation between the transmission of Zika virus and these epidemics. So, coming back to our work, the main point concerning the vaccination of dengue is that at the very beginning, the production will not be enough to cover the population. So the question is, which people we have to vaccinate? And if it's the same strategy for all places, what our results demonstrate is that you can look at the different places. It's not so easy to implement, but for example, for some cities, you can have a smaller interval of age than other cities. So since the production is not so big, it could be useful for people from public health. So,
sorry, but what is the reason why vaccination is not recommended for individuals who haven't had a dengue infection?
Why?
The point you mentioned
in the first, that's not recommended.
It's not recommended if you haven't had a previous dengue infection. Why is it?
I think that I don't know the immunological justification, but people have some kind of reaction that was not good and was not dangerous. I don't know if it stimulates. We can.
It makes more probable.
I think that's
anaphylactic shock.
See, maybe. But they are not, the point is that they were not expected that it happened. And the other point about this vaccine is that the efficiency is very different for the 4 serotypes. For example, for the serotype 2, the efficiency is 60%. Okay, so 60. So it's very small. And the vaccine is a chapter in some sense, because there are other problems that it's better to have a tetravalent vaccine because of the reaction, because of the maybe any kind of cross reaction. So I don't know, since there are not many students, I can go directly to the point. I will be very fast here because I was expecting that our students, so I made a very introduction concerning the modeling. I think many of you are familiar to this. There are a lot of model that became a kind of prototype of the linear population growth, the Malthus model, Verhulst, that very used to nonlinear growth, and so on. Our point is related to the Kermack and Kendrick, the usual SIR model. And also it is introduction. We will use very much the concept of the basic reproduction rate, the number of secondary infection individuals generated by a primary. So this is the very simple model. In a very simple way, we can see that based on the inequalities, you can see that these R0 may be associated to the initial number of susceptible and also to the beta, this parameter, that is the rate infection, and also to the removed rate. So it's easy. In an easier form, you can look at the fixed equilibrium that SR, and there are some susceptible individual and some removed individual, or here it's the same to analyze the initial conditions, but can come from the Jacobian. So, in general, the main point that I would like to analyze, this is a very simple application that you have some data here of influenza, and the main point, these parameters is usually well known for the problem, but the beta parameters or lambda that I will call it's not so easy to estimate. In this case, I think that they do de trás para frente. Where is they? It disappear. Okay, but they look at the data and they estimate the beta. Okay, another way to do that, the way that people from here do to analyze the R0 of the influenza outbreak in Mexico. You can look at consider that what's true, that at the very beginning of the epidemics, there is an exponential behavior. So this, I don't know what happened. Acho que this gamma, eu estava nessa. This gamma is, we call this force of infection. So you can estimate the force of infection by based on the initial behavior that R0 is related to. So we will use this kind of this approach, okay? Here, since we will work that one, do you like it, Gustavo? You see? Look at that. It's more strong, I know that. It was my student, my Mariana, that do that picture. And the main point, a little bit of heterogeneity we introduce here because we would like to consider the vector-borne transmitted disease. So the infected vectors, the interaction between the infected vectors and the susceptible humans led to the propagation of the disease, and also the opposite, the infection vector and the infection human and the susceptible vectors. So we have to introduce, here we introduce both the vital dynamics and another compartment that is related to the infected vectors. This one is we use density. So this is 1 minus V corresponds to the density of susceptible vectors. So this is the basic model, and we use the force of infection, and the point is that we look at the model, we replace the derivatives of the above relations, both to the humans and to the vectors, the infected, both of them, and we estimate the infection rate. This is a method that may be applied. And then, for example, we do two kinds of things. We analyze the R0, we can analyze the R0, and we also looking at the phase transition in order to fit the data, okay? And to calculate R0, you can calculate based on the local stability, but depending on the number of equations, may be better to use the next generation operators to calculate it, as you have done in some previous work. And then we go to the point. And this is a picture of the state of art, but it's very interesting to analyze. Here, it's not very clear, but it's the epidemics of Zika in 2015 and 18 by region, okay? In the blue one corresponds to the northeast region where we live, okay? Our state, Bahia, is in this region. And then, so it starts in the northeast region and then go to the other regions in Brazil. And as I told you, very recently, you have at least here 3 papers that they analyze if the Zika virus protect or enhance, okay, or protect or enhance. Now here the Zika virus protect population against dengue. And the other part, the dengue infection may erase or protect Zika virus. So it's very complicated point. First of all, here the gray and the red corresponds to the number of patients negative for dengue virus and for Zika virus. Here is the year, the important year, 2015. Then they observed, looking at serological exams, etc., they observed that there was a lot of negative dengue and positive Zika. And then they analyzed the proportional, from the population dynamic point of view, they analyzed the proportion positive for dengue virus, for chikungunya, and for Zika. The yellow one, it's very hard to see, is the Zika. So we have here the infection, and the dengue reduce, okay, but chikungunya also increase. They analyze, and for their point of view, it's a strong argument that it was not an effect of vector control. I am not sure if it's a strong argument, but it's an argument. But what they say is that there is, it is from Salvador, this data is from my city, Salvador, people from there, these guys from Fiocruz and a lot of authors, and they are trying to defend this idea. And these two are different groups. Here, there is a paper that's always that's related to the individual, okay? They analyze individual, they analyze in fact in vitro, and they observe that the dengue infection enhances Zika infection. And here is the opposite. So it's a kind of mess that there are different opinions, and this is why we are trying to analyze the model, okay? We would like to look at the data, to apply the model to that data, and to check if the model fits better in one case or in the other case. Maybe in a case with no effect. It's important to look at this data, some data to show that we have heterogeneous scenarios, okay? I have to say something that's very important. Although we are using this data, we are not completely confident to this data, because at the very beginning, people do not know what is Zika. What was Zika? People do not know how danger it is. So there is a kind of mix, maybe a kind of mix, but there are the data that you have, because you do not have epidemics of Zika after that. Sorry, Natalia.
How do you diagnose a case of Zika and a case of dengue? Or rather, these data that you have, what kind of diagnosis do they take into consideration? Is it a clinical confirmation of some sort, or is it just based on symptoms?
This data is based on symptom, but some data are checked from the serologic point of view. The best data that you have now in Brazil, not in Brazil, but in the group with whom we work, is data from chikungunya. I think that in the next years, we are construct a very huge data bank of Zika. All of things relate to Zika. There is a place now in Salvador that is a center of data of public health that is related to Fiocruz. And they are doing a very huge data bank of related to Zika. So this is, we are, some sense, we are after, behind the situation. From clinics, from hospital, they are trying to integrate the data. There are some people from computer science that are doing this kind of integration and so on. But here is more from the public health system, government, and you have this kind of scenario. This is a city in Bahia, for example, with this population, and you have very similar scenario. Here, for example, we have the peak of Zika is, there is a time delay between the peak of Zika and dengue. And then you have, for example, different scenario. Here in the northeast of Brazil, Belém, and you have more Zika than dengue, then you have more dengue than Zika. And so there are a lot of scenarios. We tried to, Daniel calculated the force of infection of Zika and dengue that we will use. And Goiânia is in the center part of Brazil. And we have used the model proposed by Lourdes, and that we consider that she used this model, she proposed this model motivated by the serotypes of dengue that's very hard to have data about it. But when the Zika virus infection began, I said, oh, it's very nice to use this model to analyze Zika and dengue, supposing that there is a prevalent dengue infection, a prevalent serotype. So the primary infection, the removed from from one virus may infect by the other virus, may be infected by the other virus, and there is the infection rate may be multiplied by a parameter that's the most important parameter for us. That's the sigma, that we'll call the co-circulation parameter. You have this effect from 2 to 1 and from 1 to 2. So we look at the model. This is the model, the deterministic model. So we consider both situations. So we have a vital dynamics, and you have the primary individuals infected by 1 or 2, and the idea is that it's exactly the same of the more simple model that I showed you, but the new term is this one. And we consider that the infected population is the primary infected plus the secondary infection. So what's the situation that Lourdes consider? If there is a partial protection, sigma is between 0 and 1. If it's increased susceptible, sigma is plus 1, is over 1. The total protection, sigma is 0, and no cross-immunity, sigma is equal 1. So all of these scenarios, and first of all, we analyze, before looking at the data, we analyze the effect of sigma from the theoretical point of view. And the first thing, if you have an infection 1, the virus 1 and the virus 2, if sigma is over 1, the effect from 1 to 2 is to increase the peak, for example, and for sigma smaller to decrease the peak. It's one effect. This effect may be a continuous effect. Okay, there he looks at it. Daniel have done this graphic. It's very simple, and we observed also a more complicated effect. This is the effect between related to the time delay between infection. Here in blue, you have a very small infection, and sigma is equal 0, but sigma is equal 1, it increases, the peak increase, and there is a time delay, depending on the other parameters. Then it increases more, but the time delay is reduced. This kind of very nonlinear effect that we see here. So these kind of scenarios that I showed you, maybe it's not, we can't say that is related to, but this kind of thing, this time delay may be related to the effect of cross-immunity. We don't know. Then we look at data. To look at data, you have to look at the parameters. So some of them, as it's usual, we fixed. We consider the interval in the literature. Look at the Zika recovered rate. It's different from dengue recovery rate. This is different, for example, from our model that the recovered rate to one serotype of dengue and the others almost the same. Here it's a little bit different. And we consider the dengue and the Zika human infection rate. We calculate based on the model and based on the force of infection. And there is a very important parameter that is the report rate, because there are a lot of subnotification. This is a problem. So we get in the literature with the interval of the report rate. It's much bigger than we imagine. A lot of papers they analyze. There are recent papers analyze this, and we consider this interval that you can have very big subnotification rate or very small report rate, and you have to consider it in the model. So this is one example. Flavia is on this kind of simulation using the data, but also trying to consider consistent restriction to fit the data. It's not anyway, it's not a very, without criterion. Without criteria. We are trying to do this criteria and the other information in the literature. So here we have this, here you have the data, and here is the fitting of the deterministic model, okay? And we observed not only in this case, but this is what we are trying to analyze for a lot of data to see how is this behavior. Okay, and for example, in this case, the results indicated that Zika affect dengue as protect against dengue, produce a partial protection against dengue, and dengue a total protection against Zika. at this example. So we analyze a lot of examples, and the idea is to do this, to apply this kind of methodology. So the other things that we are discussing here is to analyze the local stability of equilibrium. In Lourdes' model, it's important to say that the R0 does not depend on the initial condition. So you can calculate based on the methodology that I present before. And at her paper, we have the same numerator, but you have only these two terms, okay? These terms related to here, V0, I, and J corresponds to the initial quantity or density of vectors. It's very hard to estimate. We are trying to think about a simplification here. And this R0 is related to the removed. This is important. For example, we have a lot of data. Think that G corresponds to Zika and I corresponds to dengue. We have a lot of data that you have some, at the beginning of the Zika infection, you have some removed people from dengue. Looking at these curves, you don't have initial removed people from Zika, but you have this. So this R, it's an R that depends on sigma. That depends on it's not a usual basic reproduction number, but it assumes smaller values if you consider the effect of cross-immunity. Okay, it reduces. You have a term over there. If you do not have this, for some epidemics, for example, for this one, considering the report rate, the quantity of removed individuals from dengue is very small. So it's easier, and we come back to the relation that is produced by Steva, and that I simplified a little bit more here because we assume assuming some parameters, there is a term that do not influence to the results. So in this case, you have coexistence of virus in the stationary case. Otherwise, there is a prevalence. So this is an example of two seats that behave like this. If you have removed, as I told you, we recalculate the threshold of co-circulation parameters. Then, Flavia should talk about it, but the main idea is to analyze an stochastical version of the model. The main idea is to get the fluctuations that are presented in the data. And so this is a kind of individual models, is based on individuals, and they reproduce the rules that if we simplify, goes to the deterministic version of the model. Look at the rules. They consider all of the states, and she have a stochastical vector that relates of the number of individuals in each state. So, you see, a little bit complicated, but the idea is the same. The idea is exactly the same, but the main point is that the probability transition, you have a master equation, and you have the probability transition, and the probability transition between the state is defined by these rates. So, when it's related to the interaction, we have a kind of the number of infected, maybe infected vectors, maybe infected individuals, and with the application, and she performed numerical simulation. The idea here is that it's important to look at the initial number of infected individuals and the total population. Depending on this, if it's very small, there is a lot of fluctuations. But if you look at the data that I showed you, we can present here for 10,000 simulations. 10,000 runs. We have this mini stochastical dengue and Zika. So we analyzed both. We think that it's important to analyze the stochastical version in the sense that what occurs in a seat is a realization, is a stochastic realization of the nature doing stochastic realization of the model. So, and then I will try, how many minutes do I have?
I guess you have 20 minutes more.
20, okay, great. Then I present here, the first work was not published. We are discussing here, we are discussing about the analytical form, about the fitting, and so on. But this is a joint work with people from here and from Unesp, and a student from the public health, a PhD student from the public health. This is very rich ambience because you can work with students from physics, from math, and from public health. And Luciana Cardi. The idea of this work is, what have you done? We select some cities with cases of dengue, okay? And we consider a criterion that may be consistent to apply a partial differential equations and to get our results. So cities with more than 500,000 of inhabitants and a significant cumulative dengue incidence, okay? Greater than 500 per 100,000 inhabitants. So we analyze a long time series that's completely different from the previous work. In the previous work, we analyzed an epidemics, okay? When Flavia fit the data, she selected the epidemics and tried to fit that epidemics. Now we have done something different. We analyze a long series, about 10 years, a little bit more than 10 years, and we have the data by age. You have the data by age. The cities that behave like this, there are 10 cities in Brazil that has this high incidence. So we analyze this city, 3 of them in the Northeast, Fortaleza, Natal, and Maceió. 3 of them in the center part, Cuiabá, Campo Grande, Goiânia, and 3 of them in the Southeast, Belo Horizonte, Ribeirão Preto, and Rio de Janeiro and Campinas, 4 of them. There are not many cases in the south part because of the weather, and there are not many cases in the north part because the population is smaller than, there are not too many people in the north part, so it's concentrated in that region. Then we looked,
Sorry, what aspect of the weather is important in the south?
The weather, the temperature is smaller, so there are not so many mosquitoes. So that's the point. Here you have the distribution, the age distribution, and the incident in Brazil. It looks like, here we select 4 years, and look, it seems that in the whole country, it's worse, the situation is worse for children, okay? This graphic, this is a color graphic that Cláudia Ferreira have done. You have here the year, and here you have the proportional in the interval in the age interval, 5 years for each color, okay? So you have a very heterogeneous and there is no specific characteristics, but it's a mix of the whole country. And if you look at each city, I will show directly here. Look at that. We have 3 cities, and you have different scenarios. For example, here, in these years, you have more children, okay? Here, it's less children. Here, Rio de Janeiro is more heterogeneous. So you have different scenarios. And then we use the model and the methodology proposed by Gustavo and Lourdes. Lourdes is also a co-author here. And the idea is that in this model, this is a partial differential equation, a very simple model, but get the main idea that you have to consider. You consider here the age and time, and look at that. It may have a vital dynamics. I think that's not a very strong influence, but the main idea here is to consider the effect of vaccination. Sigma A represents the age-dependent vaccination rate, okay? And it reduced the number of susceptible, it increased the number of removed, and concerning the vector, we consider the integrate humans that infect the susceptible have to be integrated. So, the calculation that they have done is to consider the basic reproductive number related to the vaccine. This is, there is a huge calculation in their paper that you can, but the main point is that minimizing R0, the idea is minimizing R0, corresponding to maximizing a function of age that represents the protection of the population. And this function is related to a lot of parameters, but the most important thing is to consider the proportional of cases here and to integrate it. The point is that when they have done in his work, looking at Mexico, looking at the data from Mexico, they fit this function. They have done an analytical fit of this function. In our work, instead of fit this function analytically, we tried to fit this function. This is the proportion of case, this is the function, okay? And you calculate the derivative and we estimate an interval and the optimal age of vaccination. When you have done this, we do that to each year. This is why you can use this model like this without the vital dynamics, because we analyze the model and get the result for each year. And to do that for each year, I will try to explain. We do that for each year, do not look at the number, but this is each year, and each city, and the whole country. So you have an age interval for each one. Then, after that, we consider for each city the optimal vaccination, and here, for example, if you look at the bold line, it corresponds to the median value for each city. Then here is an abbreviation of the name of each city. So the median value of the optimal vaccination here. The box represents the dispersion. Look at that. And you have also the squeeness. For example, here in Natal, you have more, the dispersion is bigger in the upper part than in the lower part. So you have a kind of squeeness. So, and we consider also the outliers. And the interval between mean and maximum are determined by the dashed line. But the main point is that the median value is different for different seats. For example, I will try to summarize here. For example, in some seats in the middle part of the country, the optimal age is around 9 years old. But in other seats in the Northeast, and also Rio de Janeiro and some seats, the median value is around 6 years old. So if you look at the median value, and also if you look at the dispersion, you have different scenarios. For example, Belo Horizonte and Ribeirão Preto, the weather is very, how do you say, seco? Faltou a palavra. Dry. So the dispersion, I don't know why the dispersion is, it's not the justification, but this is a coincidence. Maybe, I don't know exactly the reason, but you have different scenario. And this different scenario may be used to determine the interval and to get more vaccine for the places we have, when we have a larger, when you have a worse situation, but in a more precise way. Okay? You also do a calculation about the country to compare to other papers, and we reproduce some other results. And this is what I would like to conclude here. I think I still insist in link mathematical models and epidemic data. It's a very hard work because it's very, okay, it's not very beautiful. In some sense, when we work with real data, you do not have a very definitive answer, but I think that's important not only for public health, but also from the mathematical and the physical point of view. And here we present some examples that the mathematical and numerical approach may give insights to relevant points. This work there are preliminary results that we tried to work very, very hard, Daniel, Flavia, and so on, to get a conclusion, some conclusion about the cross-reactive, at least some previous insight about it. And concerning the other model, you can estimate 2 different cities around the world and also in Brazil. You can make the restriction. We can restrict less. Still, for example, for cities that you have a very high incidence of dengue, you can apply that method. So you have a lot of cities in Brazil with high incidence in each state. So it's really a problem. So some reference here, and the only word that I say that I can speak well in Spanish. Gracias por su atención. Sí. Natalia.
So a couple of things. I was surprised to see that the optimal age for vaccination that you found for Rio de Janeiro was so much lower than in other places, when you say that Rio de Janeiro has lower incidence in general.
Yes.
Why would that be?
Rio de Janeiro is here. Okay, the optimal, because it's for example, let us compare to Fortaleza. Fortaleza, the 2 pictures that you have here, okay? In some sense, what you have here in Fortaleza, you have a huge, it's a little bit more concentrated, but here in Rio de Janeiro, you have some years that it's higher. So it is expected that the optimal age is smaller than other places. Look at Goiânia. It's not a photography, a picture of that, but it reflects this density. It's not a picture. This is why it's not exactly. We have a lot of nonlinear effects here that we summarize, how do you say, that the numerical integration do that. This is what I say to people from the public health. The main advantage of the mathematical approach is exactly this. For example, let us say a very simple example. People look at incidence all the time. They do not look at the R0. In some sense, in some situation, R0 is much more important to do some actions than incidence. That's the same. If you look directly at the proportional of cases in each age, and you decide, okay, this age you have more people, so I will vaccinate here. Or if you vaccinate a large interval, you can vaccinate more than we need, and you can do not vaccinate in other places that are important because the quantity is small. So this kind of nonlinear and in some sense, sophisticated methods may traduce better. It's not exactly, but it's more rational. I think so.
It surprised me because at the beginning you mentioned that it wasn't recommended to vaccinate against dengue unless you haven't already had it.
It was...
not recommended?
Sim.
Vaccinate people
Yes. Who have not... Exactly. There's a kind of contradiction, maybe, a kind of contradiction. But there is another important thing. This is the advent of mathematical. We are supposing here a very good vaccine. That's not so the act of... Yes, the vaccination here, we consider a kind of very big... I think that's 100%. This is a very... not 100, but I think that we consider a very efficient, very high.
Actually, this model does not consider the percentage of protection against each cell.
Yes. Consider the whole.
They have the same protection, but no, this is not.
The other point is that there are there is a paper that consider all the serotypes. We are looking at, the suppositions that we have a tetravalent vaccine that its efficiency is a kind of homogeneous efficiency to all the serotypes. That's not the real case now.
And do you have a mechanism by which you produce some sort of seasonality in the mosquito population?
Yes, this is what...
And where is it relevant? Because I realize that some of the places we have...
Yes.
Pretty much constant.
It's relevant both for this model than for previous one. This is what Flavia was doing. Only looking at one serotype, I have a previous work, an old work 10 years ago, that will take into account the seasonality. And mainly, what we have observed is that the rainfall is the most important thing, okay? We are trying to also to see the different scenarios and the RT, the R0, not R0, but R that depends on T, for different cities, and to try to do a kind of, not correlation, but to do analysis, looking at the temperature, the rainfall, and the humidity. It seems that the other people concluded that the rainfall is very important, and may produce different effects. We are talking about this.
About the actual shape or the precise shape of the forcing that would come from the mosquitoes, but rather how you put it into the model.
Yes.
Because I like quite a lot the way in which you model now the creation of vectors.
Yeah.
As, through contact with cases, with human cases.
Yeah.
And it's not very obvious to me how you would be modulating the mosquito population itself. No? Because
Yeah.
right now the assumptions are.
Yeah. Flavia? Yes.
So we tried to put a variable population of mosquitoes, of vectors, inserting a seasonality depending on the rainfall. The problem is we are trying to compare with data, and we don't have so much data of long-time series. So
For
we
this
kind of
first.
insert a lot of parameters, but not so much data.
For
But
that one.
we have one city that we have like a long data, but it has like some, like this year that has no data. So it's kind of complicated. We have done some progress, but for now, since the most of cases we have data for just 2 years, we are not using it. But it's important. It's interesting to look at. Maybe we could try like for this city we will study the seasonality because we have the data, but this can be done like in general because you don't have data to compare.
And it's
And
not.
we have like more
From the
parameters.
type of data, that's quite.
Yeah, but it's
Yes.
interesting, and what you see when you put the seasonality is that then you can see like first when you don't have, if you begin with a scenario without any infected, then you have like a first large peak, and then the other peaks are occur one peak by year, but way smaller than the first one. Still they are there, but way smaller.
And the effect of rainfall is very interesting because in the majority of cases, we have a time delay between the peak of rainfall and the peak of dengue, the epidemics. But it's interesting because what's natural, what's reasonable is to consider that the peak of dengue comes after the peak of rainfall. Do you agree? Yeah. Because the rainfall, yes, it's reasonable, but in some cities it's the opposite. Because the rainfall is so strong that it's, how to say, arrasta, yes, they kill. So it's a little bit complicated, but it's possible.
Becomes something endemic, like not every year. That more or less what you see, like, okay, we're not feeding data, but we know that every year there is a time of the year that you have more cases of dengue. Even though we don't have the data, you know this more or less by the idea of what happens. But like of the data of one city is more or less what you see, but you can't really fit anything.
Okay. Thank you.
¿Alguna otra pregunta o comentario?
Solo una curiosidad, en estas
Sí.
ciudades que notabas diferentes patrones con muy poca población, ¿es muy diferente el clima?
Aquelas não selecionadas, não, dentre essas?
Sí, las ciudades
Sí.
de Brasil, si el clima es muy diferente o...
Sim, é mais seco.
Tabuna e
Belo Horizonte, Ribeirão Preto, Belo Horizonte is more dry, but it's not, for example, Goiânia is dry. So,
But they are similar at least.
yes, they are similar. They are similar.
It's very nice to cover them
By the here the similarity, yes, and the effect of this one in this work it's possible to it's reasonable to consider the seasonality because we have a long time series for this one. For this one.
Yeah, because then you have average of 7.
But some other character is very important. For example, Belo Horizonte. Belo Horizonte was very. Belo Horizonte has a very good program of vector control, better than other cities in Brazil. Okay, there are cases and they have how to say prefeitura, they take care and the vector control is better. So maybe different, yes, causes of this. But it's interesting that it's so heterogeneous. The data is heterogeneous, it reflects, but you can estimate better. Yeah, ok.
¿Alguna otra pregunta o comentario? Siendo así, muchísimas gracias.
Gracias.
Gracias a ustedes por haber asistido. Que tengan muy linda tarde.
Cumpriu o tempo, hein? Cumpriu o tempo bem.
It's time.
Perfect.